Today's lecture is on this subject, value network mapping, and the whole idea is how do you take the principles of value stream mapping and then adapt those principles to create a method which is stronger, more capable than value stream mapping when it comes to mapping all the value streams of a complete product. Now in this case the product is maybe not as complicated as a 737 or an excavator. It is an industrial scale that is fabricated at a local facility. But again, the idea is that you cannot use value stream mapping and map only a portion of a larger product. And then in the case of a job shop, you cannot take value stream mapping and map two components just because those components are being ordered from the job shop by some defense aerospace prime, and then tell the job shop now when you make improvements in your entire facility, you can just use whatever improvements are being recommended by what our value stream map tells us for two of the maybe 1,000 components that you produce. So this method that I have developed, value network mapping, is essentially taking the principles of value stream mapping, but the methods and tools being developed or that have been developed are computer aided, because there's no other way that you can essentially handle the complexity of mapping and scheduling and designing a layout to produce an entire network of interconnected value streams. So this is something which you will see in a typical value stream map. In fact, this has been taken from the book Learning to See. TWI Industries is a very nice case study that the book talks about. But again, let us be realistic. In most job shop environments, there will be many customers. All of these customers will have their own due dates. So there really isn't this nice, beautiful structure that you will see in a job shop environment. You could have many shipments being made daily, and you cannot essentially say, I will create one value stream map and have that apply across the business. Similarly, on this end, when you look at the suppliers, you could have lots of suppliers, heat treaters, oxide coaters, parts makers, and they are not going to essentially commit to a devoted, dedicated schedule. They will basically say, look, I can heat treat your parts when you send them to me, and I'll send them to you when I heat treat them. You cannot see that I will use value stream mapping and then isolate a particular supplier for a couple of parts and then apply the whole improvement methods for just a single supply and a single customer. In fact, the bigger difficulties that I have with value stream mapping is here, right here, in essentially the product realization portion of the value stream. You are not going to see such simple bills of materials. You cut the bar stock, you weld them onto a machine forging, you weld them again, grind them, then send them to an outside paint supplier, then bring them into assembly and then ship the parts. Which job shop will tell you that we only make two brackets, left hand and right hand, and that this map represents the physical flow of all the products through our facility? I think that's unrealistic. On top of that, production control being done through MRP, I think it's suicide for any job shop, any high mix, low volume manufacturer to subscribe to that scheduling logic. MRP is fundamentally wrong, and you would like to be using finite capacity scheduling. Again, it is not as simple as sending dispatch lists to a few work centers. These dispatch lists may be sent to numerous work centers. So the difficulty I have with value stream mapping is that it cannot handle a complete facility with 50 to 100 work centers. It will have hundreds of such individual value streams which will be making their way through the same facility. And these little bills of materials, they'll be far more complicated, far deeper and far wider. So value stream mapping fundamentally is, I think, a flawed analysis tool, and that while value stream mapping may apply to a limited portion, a repetitive long-term agreement portion of the entire product mix of a job shop, it's fundamentally something which should not be used, and therefore this whole method of value network mapping was created. So here's a future state map, and again, this future state map is okay when you're trying to go from a current state that produces a left hand and a right hand bracket, and you're trying to go to a future state where you create this dedicated production system for just those two brackets. But again, in a job shop, here are some challenges. You will not be able to map the entire network of value streams of all active part numbers that are active on any given day in any job shop. So the value stream map itself is incapable of capturing the total logistics of the job shop. Then take this portion of the upstream process of the value stream. You will have a machine shop, you will have a forge shop, you could have a sheet metal shop, and there'll be many more complicated value streams which will be flowing as far as sending parts to the welding and the grinding department. Then just look in welding itself. You're familiar with the concept of group technology. When there is a high variety of weldments and high variety of welding processes needed to make those weldments, you cannot just have one single cell. Group technology has to be used, and then you will try to design flexible welding cells, but then each cell should be capable of doing a certain family of weldments, both in the geometry they do, the type of welding they do, and the tolerances and the volumes in which they produce the weldments. Similarly, in assembly, in a high mix make to order environment, you may not have a single assembly cell. You may have multiple assembly cells. Once again, it is not a trivial problem to apply group technology to be able to create flexible assembly cells. So again, this is the background for value network mapping, that the method of value stream mapping is correct. It has the fundamental message that sometimes when you visualize a production system, you arrive at nice ways to improve the production system. But again, if the method is incapable of mapping a complete production system, as is the case in any component producing job shop or any make to order product fabrication job shop, let's look outside of the Toyota production system. Let's look outside the simplistic lean tools, and let us develop and implement those tools which actually work in complicated value stream mapping problems. So here are some icons. These are all very pretty icons. I think they're very effective. But again, most of these icons mislead you into believing that the high mix environment is easily capturable with using the best practices and systems that are embedded or behind these individual icons. So again, inventory triangles. You don't know how much inventory you will be holding in front of a welding department. It completely will change day by day, depending on the products you make, the volumes associated with each order, the due dates. Push arrows, yes. If a job shop is arranged by process, of course you'll have push scheduling. But do you want to really draw these arrows on a existing layout? You'll get a spaghetti diagram. It will be complicated. Of course, if you want to see icons that I have developed as you would in the principles of value stream mapping, but these icons are able to capture the complexity of a true job shop, I'll be happy to send you a chapter from my book. It's a small book I wrote on value network mapping. All I've done was I've said, if I were to create icons that could be put, say, into an ERP system or on a desktop, and you could have displayed a complicated network of value streams using those icons, then this is how those icons would be set up, and here's the data which would be kept behind those icons. So while these icons are inspiring, a big issue is that many of them either are inappropriate to a job shop environment, or they need to be completely replaced and reprogrammed with computer enablers that would in effect capture the details behind the same icons in a value network map. So again, talking things like first in, first out, you are not advised to implement first in, first out in a job shop. This kind of dispatching logic is not correct. You would rather use earliest due date or critical ratio, or there are other appropriate scheduling disciplines as far as ordering inventory or orders in queue at any work center. Similarly, these icons which have to do with Kanbans, I think that in a job shop environment which is make to order, you do not wish to impose certain fixed lot sizes in certain scheduling disciplines. The biggest thing is make to order. So there are appropriate scheduling mechanisms, there are appropriate inventory management mechanisms that you would use in systems which are not like Toyota. So that's again, I'm leading up to why value network mapping is radically different, even though it's inspired by value stream mapping. As wow, if you can visualize a complicated production system, who knows, you may find appropriate opportunities for improvement. So, when you look at these icons, the Kanban post, again, this could be an electronic scheduling board. It could be a Gantt chart. The principle of scheduling and prioritizing workflow is important, but how you do it need not necessarily be the way that they do it at Toyota. Things like go-see scheduling, yes, but I can have a Gantt chart. I could have an electronic scheduling board. So yes, I do walk up to a particular scheduling board to see what needs to be done, but I do not necessarily have to be having it done manually. So that's the foundation. Why value network mapping? Let me tell you again why did I develop this method, and why are we now using this method instead of value stream mapping in all the job shop lean projects that we are routinely implementing. But the first thing is that I said we need to be able to map a complicated bill of material. So that means any product like a turbine, an army tank, excavators made by Caterpillar or John Deere, telecom equipment. I would like to map a complicated bill of material in entirety, because that's what defines the substance, the DNA of a product. I would also like to be able to handle hundreds of components. So we are doing a current project where the parts item master is like 2,300 routings. They make all those 2,300 routings. So when we use value stream mapping, we are essentially saying we would like to make it possible that you look at everything it takes, the production system it takes, to make a family of similar products with all its components, or if you're a machine shop making hundreds of different machine parts, we would like to put our arms around important samples of parts, part families, and then give you improvement ideas that would impact all of the parts inside the family. So that was the first goal of value network mapping. Map a complicated product, or map a large sample of components and then take a decision on what to do to improve the speed with which we produce them, the lowered amounts of inventory you have to keep, where the bottlenecks have to be managed. Far more important is this quote from the book, Rother and Shook. Of course, I have the older edition, but I believe that this same quote has been maintained even in the new editions. So the developers, Mike Rother and John Shook, what they write is, many value streams have multiple flows that merge. I agree. If you look at products like tanks or scales, of course they have components whose routings are identical, or they'll have a typical go-into structure. So components will become sub-assemblies, will become the final product. So yes, you will have flows that merge, and that flow would look like this. This is the main product, and that builds up into multiple sub-assemblies, and that's how it goes into. This is a structure called the goes into chart. It is nothing radically new. We industrial engineers have been working with these charts. We call them operations process charts, assembly precedence diagram. It's standard industrial engineering charting verbiage. So here's my bigger concern. The authors say draw such flows over one another. How can I draw them if I don't know, first of all, that all these value streams correspond to identical routings? So unless I've done some group technology, unless I know that these value streams have identical routings, I'm not going to be able to overlap these value streams and say this value stream actually corresponds to a manufacturing cell which will produce this family of parts, all of whom have the same routing. So how do I know which ones to draw over? Far more scary is this other statement. But do not try to draw every branch if there are too many. Choose the key components first and get the others later if you need to. When? When you find out that a kit is incomplete and that parts are missing. So, you cannot ignore any part. that belongs in a kit which goes into assembly or which goes into welding. All of the parts have to be available. So this cop-out, which is, well, ignore some branches, and only work with key components, is absolutely incorrect. I think that we need a method which is able to account for all the components, all the sub-assemblies that make the final product. So why? Because there's a very difficult problem. The whole issue of having to coordinate and synchronize the production of all the components which comprise sub-assemblies, especially if those components have common resources, then scheduling is an extremely important, unfortunately hard problem. How should a particular work center prioritize different components that it receives in queue? And frankly, I feel that this little chart here, we industrial engineers have been using charts like exploded bills of materials, assembly precedence diagrams, operations process charts since ages. So we can easily take those charts, and if we wish, we can give some icons. The point I'm trying to raise again is that value network mapping is nothing new. All it has done is it said, well, if non-industrial engineers have come up with a very good method called value stream mapping, let's use industrial engineering charting methods. Let us overcome all the drawbacks and incapabilities of value stream mapping when it comes to synchronizing and managing and designing facilities that will make hundreds of different components, or they will make custom configurations of a variety of products. So here's our goal. And again, I would like to put this slide and these 3 bullets in the context of the 5-step lean thinking process that Womack and Jones put forward in their book, Lean Thinking. Basically, they had 5 steps. The first step was define value from the point of view of the customer. So quality, cost, delivery, that's universal. Even the job shop is going to have to work with those metrics. But the second step is identify your value streams. So that's this one, that what we would like is for the value network mapping method to be able to understand what are the families of parts to work with, or what are similar product configurations that should be worked with. So think of it this way, that our goal is to develop a method which will be able to implement step 2 in the lean thinking process. Identify the value streams that you wish to improve. Step 3 in their thinking process is, once you've chosen the value stream, try to achieve flow inside the value stream. That has to do with firstly layout, material handling, ergonomics, shop floor control, visual management, pretty much standard industrial engineering functions. So that's what we are trying to do with our method also. Basically use this software tool, production flow analysis and simplification toolkit, to essentially implement step number 3 in the lean thinking process in high mix, low volume facilities, especially job shops. And fundamentally what we're doing is, we're trying to implement these basic industrial engineering mapping methods and analysis tools which have been used for decades. That's all we're trying to do. Just make those IE methods come to life in high mix environments, and since software will be used, develop and validate that software. And then finally, step 4 in the lean thinking process is pull schedule inside the value stream. Now, pull scheduling is not necessarily the only scheduling method. You can do finite capacity scheduling, you can do convip, constant work in process scheduling, you can do drum buffer rope scheduling. Point again is that once you have designed the layout for flow, even in a high mix environment, you have to do something as regards scheduling. And so that's what my bias is. I'm completely aligned with finite capacity scheduling methods to do essentially resource constrained release of work into high mix environments, primarily driven around due dates and finite constraints at bottleneck resources. So our goal essentially is, just like Womack and Jones said, there's a 5-step lean thinking process, and value stream mapping is a key component of the implementation of their lean thinking process. Same thing. This is step 2 in our value network mapping method. This is step 3 in our value network mapping method, and this is step 4 in our value network mapping method. And then since we go part family at a time in step 2, Step 5 would be go back, find the next part family, and keep on. So this is essentially what value network mapping also is doing. It's just developing different tools to handle the complexity of high mix, low volume. So please note, this is what I'm going to try and show you, that when we implement value network mapping, the tools that we have developed will essentially try and tell you how to locate the work centers on the map, how to map the individual routings, not lose them. Like if you have to merge, you will only overlap identical routings. How do you know the families of parts, which is group technology? How will you design the entire facility based on the concept of point of use? Then, where would you put your supermarkets? Where would you put your buffer inventory? How do you schedule and synchronize parallel value streams? And then finally, just as value stream mapping has a measure called value added ratio, how will you compute a value added ratio in the current state of a complicated value network? So I will do my best to show you how, with the value network mapping method, we do these things which I recognize to be what even value stream mapping does in simplified systems. So let's look at what a point of use integrated facility would look like. And what you're going to look to is this book by John Costanza. Of course, he's passed away, but then his work continues with other groups. He came up with a method called demand flow technology. And again, I believe that value network mapping is essentially saying that the goal is to design this kind of a facility, no matter how complicated the product mix or how many components are being produced. So, if you look at this diagram from his original book, he's pretty much figured it out. What he's saying is that this is where the main product, this line is where the main product or product family gets produced, right? So essentially begins with frame assembly, then final assembly, pre-powered test. He came from HP, so naturally I think he's looking at computers and other computing systems. So this is the main product. Now, once you explode the main product into sub-assemblies and modules, that's basically advising you where modules or sub-assemblies have to be delivered to the line. So this is basically an explosion of the main product into sub-assemblies. And then as you explode the sub-assemblies into lower level sub-assemblies or components, you start seeing how the complexity at the components level starts exploding. And so all that he's getting at is, once you explode the product into its bill of material and lower level components, what you have is the logical explosion of the product into its components, and then as you get into upstream processes which will make the components and the sub-assemblies, that's where you wish to create your cells. And this is again what Ono said in his book, Toyota Production System, that you should build the facility and schedule the facility as per the logical building of the product from its components into its sub-assemblies into the final product. And so appropriately then you will say, well, this is how I will design my sheet metal shop, this is how I will design my machine shop, my injection molding shop, and so on. So if you look at Toyota's San Antonio facility, this is the main assembly plant, and then we've basically taken these major modules and they put their key suppliers right around the main assembly plant. It's logical. It just makes complete sense. The difficulty is that most managers, when they are faced with the complexity of organizing the lower tier production facilities where the components and sub-assemblies will be made, because they don't believe in group technology or they don't know how to implement group technology using production flow analysis, they outsource that difficulty to suppliers. And then suppliers don't take the time to implement group technology, and that's where the chaos remains. So job shopping essentially is figuring out how to adapt lean in those lower tier levels of product build, and then saying, well, in assembly and tier 1 you use the Toyota methods, and then in lower tiers you basically implement job shop lean, industrial engineering, quick response manufacturing, constant working process, whatever you wish to do. But the idea is change how you implement lean in the lower tiers of the product's bill of material. So these are again some charts which you will see from Costanza's book, and he's basically said, explode your product into lower tiers of your product, and you will have a logical way as to how you organize the lower tier production of the components and the top tier production of the product. Again, some pictures, I don't have many details, but it makes complete sense. And fundamentally, the sense is, look at your MRP system, look at the bill of material, look at the routings of all the components that have to be made that are not basically hardware items which you're purchasing. Replace those components with the routings. You will get something called the indented bill of routing. It's essentially what we call the operations process chart. And then use the operations process chart to essentially create the value network map. And then with the value network map, design the layout and schedule the facility. So to quickly give you an overview of this method of value network mapping, let me give you a simple example from almost 20 years ago. So very simple, how do you draw the map? That is, what is the skeleton of the map when you have the bill of materials for the product and you have all the routings for the components and sub-assemblies and the final product. Okay? So take the product, find its bill of material, find all the routings of the components, the sub-assemblies and the product as they go through various work centers in the facility, and then how do we draw the map? So this would be the first view. Like it's a bill of material, this is like a wound rotor, that's the main rotor. It explodes into two big sub-assemblies. Each sub-assembly breaks out into, like this one breaks out into 3 components. This major sub-assembly breaks out into individual components. There's a big sub-assembly here. This sub-assembly actually is built up from this lower tier item, and this item itself is built up from 2 individual components that get produced. So this is your basically exploded diagram of the wound rotor. Okay, that's why it's called the goes into chart, that these things go into and become the final product. And the bill of material is just, I need these items in order to make the rotor. So next what you do is you find the routings of all these components. So here's basically what was given to us. Take this component, essentially starts at this work center, then goes to this one, this one, this one, this one. That's where the component, this component finishes. But what you would like is that this work center be near the first work center where this subassembly is built. This subassembly is built from this component, which basically goes through this work center, 130. Notice that this component is also going to go through this work center. So automatically you can see there is going to be a scheduling competition at work center 130. And you know that to minimize work in process, that is to minimize the time that this subassembly is not done, you would first try to run this component through this work center and then run this more complicated work center. Now that is SPT. Sometimes the logic would be just the reverse. It may be run this complicated work center, complicated routing through work center 130 and then run this. The point again is that you can see automatically just at this level, because these 2 components which go into this subassembly are going to have to visit the same work center, there is a scheduling difficulty. And I think that something like finite capacity scheduling is the only way that you can essentially synchronize the production of these 2 components. Now, these 2 components must be delivered where? To the location of this work center, because that's where they get joined, and then once it gets joined, they get run through these individual work centers. So it is important that once you have the exploded structure of the product, now for each of the components which is produced in-house, you essentially attach now the routing of each of those components. So again here, these 3 components have to be produced. And when they get produced, they should be delivered to work center 1000, because that's where they'll get joined, and then that joined subassembly is going to go through all these steps and then will arrive at the location of the wound rotor. So strong advice to you would be bill of material and then attach the routings of all the components in the bill of material that you have to make. And that effectively, what you see here, by combining the routings with the bill of material, what you get is the operations process chart. This is the DNA, this is the starting point for any of the value network mapping work that we do. But it's all classical industrial engineering. Now, what you will see is there's a tendency for us to merge these routings as soon as they have shared work centers. Over time, I've learned that what you would like to do is keep all the routings associated with this subassembly separate from all the routings associated with this subassembly, even though they will have shared work centers. Let me show you what happens if we just go ahead and merge all the routings just because they have shared work centers. You will get, you will see that these are all the individual components, and this is where they all have, their raw materials will have to be delivered to various work centers. So this component gets delivered to this one gets delivered here. So these numbers here represent the individual components which appear. You see these individual component numbers here? That's the component numbers here. And what we have done is we have merged those routings into what we call from two charts or spaghetti diagrams. But automatically you can see there is so much commonality of work centers. Look, 8415 is here, 8415 is here. There's going to be some competition when those two sub-assemblies hit. Work center 10770 is also used here, 10770, right? So that you can see there's going to be competition. Then look at other work centers. Look at work center 8450. It's used here to make these components, and then 8450 is used over here to make these components. So this is the reality of value network mapping, that when you try and work with a complete product structure, you're going to hit this issue of, well, am I going to duplicate shared work centers which are across multiple sub-assemblies or sub-networks, or am I going to aggregate them in the name of efficiency? Strong advice is, please do not go with this efficiency mindset. Please go with focus and flow. That's exactly what Toyota has done. What they've done is they have looked at the particular process that's shared and said, can I right size it? Can I buy cheap equipment to do the same work? The big thing is separate individual value networks, especially if those networks correspond to sub-assemblies, and then produce sub-assemblies in mini focus factories. So this, what you're going to see next is an example of an actual product that I worked with. Actually, we cut our teeth on value network mapping with this particular product. So this is essentially, you will of course have this PDF file, but what you see here is all these numbers. These numbers essentially are unique levels of the product. So this 22 represents the final product. So 22 was a portion of the product which had to be used for scheduling. Okay. Then if you look down here, you see the indented structure. This is called the indented bill of routing. So at level 1 are those items which constitute the final shipped item that goes on the truck that gets sent to the weighing location of the interstate. So this is level 1, and then between this level 1 and the next level 1, you see everything that has to basically go in to make this level 1 item. So let's see what that means. This level 1 item is comprised of all these level 2s, right? Some of these level 2s are basically like the frame product, okay? That's based on welding. Now, these level 2 items, this level 2 item is actually having level 3 explosion. Why? This level 2 item, if you notice here, is an angle. It's a cold rolled steel angle. But how does it get made? First, they go and get the sheet stock of a certain gauge. They get the sheet stock. That sheet stock for operation 10, for first operation, goes on the shear. You see this work center 763, the shear. After it gets blanked on the shear, then it goes for the second operation on the press brake where it gets bent. When it gets bent, it basically becomes this angle. So this is, if you notice, if you go way down the structure, the indented bill of materials, these level 1 items, see this is the manual. You have to put the manual as far as assembly and operation of the scale. You have to have cardboard on the skid because that's what you're going to pay for, and you're going to make the customer pay for this item. Then you need wood to make the skid. So the level 1 items are what constitutes what goes directly on the truck, and then the level 2 items are internal to each level 1 item. And then the level 3 items are internal to the level 2 item. The level 4 items are internal to the level 3 item. So let me see if I can give an example of a level 4 item. Look here, take this case, okay? This level 2 item is built up from these level 3 items, okay? But these level 3 items, one of them is a bumper, okay? This bumper, if you notice here, you need 2 of them, okay? And it's bought, B is bought, it needs to be bought, correct? Then this level 3 item is a frame, right? But that frame has to be built up from plate stock. That's this item 900. That plate stock is first taken to the shear where it's blanked. Second step, it goes to the punch, right? And then it goes to the brake press for folding, right? So after these 3 steps, this level 4 raw material becomes this level 3 item. So it's called the indented bill of routings, and effectively this is the DNA. I strongly feel that you should spend some time when you print out this PDF file, cut and paste the 3 pages, and you'll get like an 11 by 17 size sheet. It will give you the total view of the entire product, and this multi-level bill inquiry, this is gold. Can you claim that your ERP system has the completed exploded view of all your products' bills of materials, and that all the routings and the labor standards associated with all the routings are correct? What do I mean by that? Let's look at these columns. Again, I don't know the particular MRP system, but let's look at these steps. So for this operation 10 on this MIG welder, it says it takes about half an hour, 0.5 hours for that step. But where's the changeover time? So this is just the cycle time. Where's the changeover time? Where's the scrap rate? So just by programming all these columns in your ERP system's bills of material databases, I think you can easily capture all the information that today value stream mapping gurus will say all of that information has to be captured with stopwatches when you go into the Gemba. You know, this is basically an industrial engineering function. You need industrial engineers on staff who will essentially record all of these items of data that effectively appear in the process box on any value stream map, where for each process step you're trying to capture changeover time, cycle time, first time through, uptime, cycle efficiency. Is it 100% labor operated, or it's partly automated, partly manual? There's no reason why these fields in your ERP records could not capture all the information that today you're being told, go on the Gemba and observe and then collect the data. So I think that, again, making your ERP system capable of supporting value stream mapping or value network mapping is extremely important. And this is where the teaming of industrial engineers, technology for process data recording, and the operators who do the work, working in that team, is extremely important. We have to get away from this classical view of industrial engineering that we are there to make measurements, to make people work harder. I think that with Toyota, a completely new meaning has been given to team-based improvement and data collection. So this is essentially the structure, and later on in the slideshow you will see these numbers that capture unique elements or stages of the overall product. They are shown on those maps. So let's do a quick review again. We would like for the value network mapping method to essentially take care of these things, that how do I draw all the work centers on a map when there are multiple value streams? How do I keep the identity of each value stream? How do I form the families of parts? How do I design cells which do a point of use delivery of the work they do into the next level of consumption to build the product? Where do I put the supermarkets? Typically where components become sub-assemblies. And then how do I schedule? And then how do I compare the ideal schedule versus today, my performance, to make the same product in the current state? So, this is what the indented bill of routings would look like. You know, there are three major sub-assemblies. There are three major sub-assemblies. 1, 2, and 3. Three major sub-assemblies. Lots of purchase components, not very important. You know, these components could be delivered point of use by a tugger, or they could just be in racks or bins located equipment side. But this is the big thing, that try first and foremost to have three separate sub-assembly cells. Is that always possible? No. But asking why it's not possible is worth the company's effort. Okay? So, where would you put your supermarkets? Naturally in front of the welding stations. So the MIG welders here, there's a MIG welder here, there's a sub-assembly here, there's assembly here, there's assembly here. So really, you would put supermarkets here, you would put a supermarket in front of MIG welder, you would put a supermarket at this assembly. You know, it's logical. Just look at the way the product gets built, and wherever multiple value streams become one, that joint point is where you would put the supermarkets to coordinate and manage, you know, kits of parts. So that's, again, I'm not saying that it should be done, but do not merge the value streams when you know that there are critical, unique sub-assemblies. You know, look here again. When you notice these individual components being produced, they do not necessarily end at the same machine, the same work center, right? This is press brake, then there's a wheelabrator, then there's some iron horse, there's some other machine, right? There's a Viking. Why are these parts being delivered to different locations? Now, it could be there was a lack of space, but then the point again is that if all of these components should arrive at the MIG welder, why are they being shown as being stored in separate locations? So maybe there was a reason, maybe there isn't, but that's another thing to pick up, that from this initial skeleton of the value stream, you get some sense of where to put the supermarkets, okay? And then more fundamentally, I think you will see where is going to be this major issue of shared resources. See, this sub-assembly, this particular sub-assembly is built through this processing sequence, but then this sub-assembly is also built through this processing sequence. So like it or not, one of these sub-assemblies will have to wait for the other one to be done. That becomes a scheduling issue. Then, these components go through the shear and the press brake. Guess what? These components also go through the shear and the press brake. So what do? Do you design a cell which will have a shear and a press brake and be flexible to make components for this sub-assembly and this sub-assembly? Or do you have one area where it will have its shear and its press brake devoted to making these components for this main assembly, sub-assembly, and then have another focused cell or area which will then have a shear and a press brake to make this sub-assembly? These are all issues of load calculations and equipment justification. But looking at what Toyota has proven, when you go and ask, why can't I create focused areas, one for the sub-assembly, one for this sub-assembly, and one for this sub-assembly, by the time you look at the true utilization of the equipment, what the guys doing group technology and then later the guys at Toyota found out that through right sizing, through equipment utilization improvement studies, they could use existing equipment and create separate focus factories to make these sub-assemblies. But this is very important, that what value stream mapping simply fails to capture is the tremendous amount of competition that will arise and the difficulty of synchronization of value streams that will arise when components which go into one sub-assembly are using equipment to make components which will go into another sub-assembly. But this is where again, initially we used Microsoft Project to schedule this entire network, and then we switched to Preactor, the world's leading finite capacity scheduler, to again handle this issue of which components in which subassembly do I do first on equipment that is going to be required to make other components in other subassemblies. So at this point what I would like to do is exit PowerPoint and then show you how we input this bill of material structure and all the routings into the fast input file, which is an Excel input file. Let me so this is your fast input file. So here is your work center file. So these are all the work center numbers. That's the first column in that spreadsheet. These are all the work center numbers which occur in the various routings. And again, in this case, the description is the same. It's text here, it's text here. So this is the work center column. This is the description. Again, this column, these labels are going to appear in your printouts, the fast output. So what we recommend is to try and keep these strings short, whereas over here you can put the real description, bandsaw, size, capacity, etc. This column area is just a default. We thought we could make fast into a total layout design package. We ran out of funding, so at this point the area of each of these work centers is just kept as a default of 1. So when you create your input file, this would be the work center file. These are now your routings. So you can see here the part number column. This is your routing for part number TA201968. So every component that is produced in the product, it has a routing, and then the work center that are associated with each operation step is over here. So as far as the fast input file goes, these are the only 3 columns of input data you need. So look at the sequence number column. For part number TA201968, it goes through 7 steps, and these steps include all the steps from subassembly right up to assembly. So the way we use fast to implement value network mapping when there are fabricated products involved is we only capture the routings of the lowest components. We do not consider the subassemblies and the main assembly. Why? Because what we are saying is if we capture the routings of the subassembly and the product in the routings of the components, then pretty much all the components which go through a particular subassembly will have the routing of the subassembly. Again, this may be a lot to digest in an online lecture. You're welcome when we have discussions and chat groups to clarify this point later. But this is essentially the routing of component TA201968. So for its first step, it goes through the bandsaw. Second step, it goes through the 763 Acro work center, then the Viking. Then it becomes part of a subassembly which gets welded at the MIG welder. Then that weldment is ground in the wheel operator, and then goes into final assembly at the work center 811 HMLV, whatever that is. And this is your part numbers. Again, these quantities are what were pulled off the multi-level bill of inquiry. In the case of an assembly, there is no revenue. So really this field is empty. So any outputs which have to do with revenue are garbage as far as the fast output goes. So these are all the parts. These are the lowest level parts which get made that become sub-assemblies. This is their description. It's a default. We've basically kept the part numbers as a description, doesn't really matter. So once this is done, this is the input file. Next, what you want is the fast output file. So this first tab spreadsheet in the fast output file, it's called the fast analysis report. Once again, it's in Excel 2003. So once you get your output in this format, it basically is something which you can play around with, massage it. You can input this information into other packages or extract information, create another fast input file and rerun that new file into fast. You can do lots of good things. So PQ analysis is not really relevant. You're trying to make the entire assembly. Same thing with PQS analysis, you don't really need that. What you care about is this from to chart. So what you got here is, when you look at the individual quantities of the parts, this number 6 is saying, well, from the bandsaw to the 763 acro, totally 6 components are being moved if I wish to make the final product. Then 23 is basically how many individual components go from the wheel operator to the HC finished machine. These numbers, the higher the numbers, the more that you're being asked, try to put those work centers next to each other. That's your flow diagram. So once again, you're being told that these thick arrows are telling you that those work centers should be short distances apart. These thin arrows are telling you that, well, you would like to put these work centers next to each other, but really you would like the shear and the press brake to be next to each other. You'd like the press brake then to be adjacent to the MIG welder. So one of the fast outputs, basically the from to chart and its appropriate flow diagram. One is a matrix printout, the other one is a graphic printout. The thick arrows, you should try and put those work centers connected by the thick arrows adjacent to each other in the final layout. Okay. The F represents frequency. Don't use it. I don't think it's ever proved useful. We just get that as, okay, let's include that in the analysis, but I've never really used the F, the frequency type flow diagram and from to chart. This one is your classical product process matrix. So here, these are all your individual value streams. These are all the work centers in the facility. And if you print this out, it's a single page. Effectively what you're being told is, well, there are certain work centers which are common to all the routings of the various value streams. The more important one here is this one. If you notice here, in this, it's called a cluster analysis dendrogram, and this is PR2. All of these components are identical. That's what this line represents. This line here is telling you that all of these components are identical as to the work centers that they use. And you'll see later that pretty much they all go through the same sequence of the same work centers. Now, this family of parts differs by at most one center, and therefore now if you look in this PR2, this is the slightly bigger part family. So what you're doing is you're saying, well, if I try and make a few more parts, they are not identical, their value streams could not be merged, but if I could put work centers into a flexible line, I would make that flexible line make all these components. And if I wanted to make a slightly more flexible line, then this would be my larger part family. So yes, the work centers used to make this identical family of parts are not going to be sufficient, but if you added a couple more work centers, you could also make this part and all these parts, and that's why you can see in this dendrogram that this is what is called a flexible family of parts. So it's not a value stream which is identical, but these are highly similar value streams. This is again something called PR3. If you had to create modular layouts or fractional cells, you would use that. I didn't use that much for this particular application and for the implementation of value network mapping. In other presentations, you will see that like there was a case where we had an opportunity to recommend to a machine shop that if you go and buy flexible machining centers, then why don't you buy a machining center which will combine the following set of existing machines which you have in the current facility. That is where PR analysis 3 was used. So anything to do with modular layouts and fractional cells or partial cells as I call them, PR3 in combination with the from to charts is what you would typically use. This is what we used a lot for value network mapping. So I will cover this again, but what I would like to show you is in PR4, what we are doing is putting one beneath the other those value streams which, if you put their equipment in that logical sequence, pretty much all the products would flow from the left end of the facility to the right end, or the top of the facility to the bottom. So even a job shop could physically, viewed from the rooftop, be made to look like a Toyota assembly line where everything is going from one end of the facility to the other end. So what PR4 does is it puts one beneath the other those value streams which are identical or very similar in the logical flow of products from operation 10 to the last operation. So like in this case, both these value streams use the shear first, then the press brake, then of course the MIG welder because they get joined, then the grinder because that sub-assembly is being deflashed, and then of course final assembly. Same thing here. So if you go further down, you look down here now, you look at these value streams. See, they're identical. Now again, please note, this is where the limitations of the FAST software also show up, that it's using a heuristic. So if you look at these three value streams, they are identical in the sequence of steps that they go through. Ideally, I would like to see these two value streams and these three value streams, one beneath the other as a set of 5. This particular algorithm didn't pick it up. It got a little misled. It basically put beneath this value stream, it put this value stream, which only differs by the punch. But still, if you inserted a punch into what was earlier this production line, if you designed a production line which had this sequential flow and you simply put a punch between these two machines, then that line could have basically produced all of these parts. So really, if you'll see later on, this flow family, this flexible value stream, this group of parts actually gets picked up very nicely in this family of parts. So in many cases, what our students do, what we do is we kind of put the PR2, the dendrogram PR2 group analysis, we put that adjacent to the PR4. And then we kind of slice and dice, and then we manipulate the initial spreadsheet to get the final spreadsheet, and then the final spreadsheet becomes the basis for how we lay out the facility. So that's as far as the, you get the bill of materials, you incorporate the routings, you create the entire operations process chart for the entire product, then you convert that operations process chart into the FAST input file. You run that input file through FAST, you get the Excel version of the FAST analysis report. This is basically what you will get. And then, then comes really the creativity, and it's very hard to teach that, over a single online course, but, we do our best, and most cases, an OSU student working as an intern at your facility, that would be the best way for you to take your FAST analysis report and get to work, within 3 months. Really, that's typically the internship's duration. Within 3 months, this output can become gold for anybody. You just have to take that step that, hey, we can do something with value network mapping that our little method of value stream mapping taught to us by our local lean consultant was not able to do. So once you get these outputs, you go back here, and we are back in our presentation. So this is the data analysis. So this is basically what you get from your FAST analysis report. Now you'll notice that this routing is identical to this routing, is identical to this routing, to this one, to this one. Okay, so over here, even though these are raw routings, just by eyeballing, you'll quickly notice that there's a family of parts, these 3 parts, and these 3 parts. These are identical, so you would merge those value streams, but then this particular routing, and I think this routing, they're slightly different. So you would not merge them. You would keep them adjacent to the value stream which represents these 3 parts and these 2 parts. So that is the beauty of the value network mapping, that You know which identical routings can be merged and put on top of each other. Just put all the part numbers beside them. But you also know a part family. That means you know which value streams are similar, but you can create a flexible cell to produce all of them, but you retain the identity of those value streams which are not identical. Okay? This is your from to chart. This is something which is, it's a Q type. So if you notice, when you do assemblies, the dollar type from to chart may not be most relevant. One way we have used the dollar type from to chart is, we looked at these individual value streams and then we computed the total labor content of the work which would get done in these value streams. And so instead of revenue, we basically put the total labor content. And so again, the thought would be that those value streams which have a high labor content and a large number of processing steps, you wish to focus on those first, because those are probably killing you in terms of response time or in terms of kits not being complete, because those complicated value streams were not done quickly enough. This is your PR2, this is your grouping. So you can see again, you saw this already in the Excel version. This is something which came off the online version. We just copied the image in. So this is a very strong family of parts. This seems to be a separate family of parts. The cell or line which would produce these parts would probably merge or be adjacent to the cell or line which would produce these two parts. Okay, and then similarly, these are the parts. They themselves seem to form a separate small family, and then they would essentially be produced in the factory which would produce all these parts. Again, this may be a little too much to swallow. The point again is that you need to look at families of parts. You need to look at which value streams are identical and which ones are similar. But you need to maintain the uniqueness and the identity, because all of these value streams become kits that become sub-assemblies. And if parts are missing, you are not going to be able to complete a sub-assembly. So I think that the authors of the value stream mapping book are making major assumptions just because their method cannot handle complexity. So this, if you notice, is really where the rubber hits the road. So let's go back to what we had said about the contents of a value network map. So the first point was, one, in a value network map, given all these routings, given the bills of materials, where do you locate the process boxes representing the various work centers on the map without creating a spaghetti look? So with PR4, this is what you would do. You would draw a process box. Inside that process box, you would name it as the shear, right? This would be, you would draw a process box and say shear. You would draw a process box next to it and name it punch. Then you would draw another process box to its right and call that press brake, okay? Like, so what we have done with the fast output is, because it has put one beneath the other, those value streams which are identical or similar effectively are being told that if you put a shear here, then all these individual value streams and their inventory icons would essentially all merge and go to the shear. If you put a punch here, these three value streams would be dedicated in setup and capability on this punch, right? So PR4 effectively is one way of drawing the process boxes. So that's the whole idea, that use PR4 and aggregate consecutive appearances of the same work center, and once you've aggregated them all, try and put one process box in that collection. Okay, so effectively you are capturing almost like a blueprint of how the facility should be laid out. And so the map where you draw these process boxes representing the various work centers, effectively that map could be your ideal state of how this make-to-order facility should be designed. Okay? Let's do the second content of the value network map. How do you show the exact routing for and identify with the part number each value stream? There you go. Every row in the spreadsheet has the component number, okay? And then that component has its own routing. So effectively you've been told, draw the value stream for this particular part number here, draw the value stream for this part number over here. It has taken care of that problem. So each of the individual value streams is listed, each of their routings is listed, but if they have common work centers, they are shown entering a single process box. Okay? So that is number 2. Next, how do you identify the families of parts and sub-assemblies based on similarity of their manufacturing routings? So remember in PR2, this was, for example, a pretty cohesive family of parts, 1, 2, 3, 4, 5, 6, 7, 8. Well, keep these part numbers in mind, and if you notice, in PR4, this collection of value streams placed one beneath the other corresponds to a routing family. So between PR2 and PR4, you effectively are not only seeing how the value streams will go through various common work centers, but you're also being told if you were to design a cell or a line which would be able to make a family of parts, here are all the parts whose inventory locations and replenishments and coordinations should be managed. So that's number 3, that by simply eyeballing both the PR4 and the PR2, you're being told that, hey, this is where the families of parts are. This would be maybe one family of parts, this would be another family of parts. Please, you are not going to get these clean families of parts, especially when you have expensive equipment or monuments being shared across different families. But again, being able to visualize in entirety the complete coming together of all the value streams at any level, component, sub-assembly, main product, that's the beauty of value network mapping when you work with bills of materials and classical industrial engineering charting methods, and of course, software. Then, 4th question is, how do you design a point-of-use network of cells? Really, once you know these individual value streams and where they go into equipment or work centers where they get merged. So for example, the MIG welder, that's a natural location for merging. So if you had to design cells, whatever comes out of these cells would essentially go to these MIG welding points, and those would become what you call point of use. Something which gets produced from a cell should immediately spit it out into the next cell where it gets joined with other components. So this is the whole idea of the point of use, that because this little matrix in Excel is a coming together of all the individual value streams logically, you're pretty much being told that when things come out, like as soon as they come into the MIG welder, you would like these work centers to be next to each other. Like this work center is spitting stuff out to the Viking as well as being sent directly to the MIG welder. So next to the MIG welder should be these 2 work centers, and whatever comes out goes into a holding zone where the MIG welder comes out, pulls those parts in and creates a sub-assembly. So look at all the welding points. There are like 761 H stud, 764 weld M, 763 weld M, 761 assembly, 811 assembly. So this one, this one, this one, this one, and probably this one. There's a natural point of view suggestion. You just have to say, hey, when the components come off supplying work centers, they should directly go into these point of use buffer zones. Finally, this last chart helps you also to ask the question number 5 as far as the contents of a value network map. 5. Where to locate 1. The supermarkets to store groups of raw materials. Well, very clearly, if you know that this is a cell and that all these parts pretty much will all go to the shear, then you will basically have staging zones where the inventory for all these individual components will be managed. Visual displays, Kanban squares, whatever have you. So once you know your part family, because all of them get produced on the same work center, you have an immediate guidance as to which parts should have their raw materials delivered to which work center. So these 3 components would have their raw materials delivered to the punch. All these components would have their raw materials delivered to the shear. So just look at families of parts, look at first op work centers which are common in their routings. That's a logical basis for locating inventory storage points. Second, 5 part 2, where to locate the supermarkets to store kits of parts for different sub-assemblies. Once again, it's a no-brainer. Look at your bill of materials, look at the operations process chart, look at the logical sub-assembly points. Whichever work centers are creating these sub-assemblies, that's where you want to put these supermarkets. And by color coding and labeling, or having different racks or different areas for storage of individual kits of parts, you know where to put the supermarkets, right where components become sub-assemblies and sub-assemblies become larger sub-assemblies or the final product. And as you saw in Costanza's diagram, off the main assembly line, if there are modules that have to be attached to the main product, that's again a logical location for Kanban squares or modules which will go directly when supplied onto the main product. So that leaves essentially two more elements of the contents of a network map that have to be covered. 6 is how to schedule and synchronize the production of the different value streams that will have to access common work centers. And 2, once you have these multiple value streams coming together, and what matters is how much time it takes you to make the final product, how do you aggregate the good or bad synchronization of these individual value streams and compute one metric which will say, well, ideally it would take us only so much time to make the complete product. Today, to make the complete product, our records indicate so many hours or so many days. So you compare the ideal completion time with the current state, that ratio is what becomes the value added ratio for a value network map. So, see, just to point out again the difficulties which arise with, when there are similar or identical value streams, just because there are value streams in this subassembly which are identical to value streams in this subassembly does not mean you merge them. Now, there are two schools of thought. One school would say, design mini factories each for these 3 sub-assemblies, okay? But then you duplicate equipment. Another school of thought would be, no, create flexible cells. When there's a request for a particular product, each of these cells will be told, make the following components, even though the components will go into separate sub-assemblies. Rely on the tugger, the water strider, that when they arrive at the individual cells, they'll have containers into which they will put the different parts for different sub-assemblies. And then when they do the milk run, they will go to the individual cells, unhook these containers and drop off their contents to the individual cells. This is why the water strider plays an extremely important role in the context of implementing value network mapping and point of use facility layout. It's extremely important, very unique idea that Toyota pioneered. But with the FAST software, you can find out simply by naming the parts appropriately. You will know, oh, I've got parts which are from 3 sub-assemblies, but they all have identical or very similar routings and therefore could be produced in a flexible cell, but then delivery will have to be made to separate areas. So please note this, that the value network map contains similar or identical value streams. You've got to know that. Now, again, just my bias, but this is what would be my bias, that I would create a flexible line or flexible cell for subassembly 1, a flexible cell for subassembly 2, and a flexible cell for subassembly 3. But I would really work hard on saying, what do I do to put a punch here and a punch here? I think it's not a trivial problem. But how would you use FAST to design these individual areas? Again, just take the routings for this subassembly separately, create its own input file from the original FAST input file, run it into FAST, get the outputs. Do the same thing for this sample of routings, do the same for this sample of routings. So FAST is pretty flexible. You can design the total product or you can design the individual cell. So the aggregation of the value streams into sub-networks, the whole idea is to create these flexible, separate focus factories. So how to design the facility layout? Go back to guideline number 3, step number 3 in the Womack-Jones process. How do you achieve flow inside each network of value streams? This is how the facility layout was. If you overlaid the from-to chart, the Q-type from-to chart, and there were thick arrows for the high values in the from-to chart, there were thin arrows for the low values in the from-to chart, but you mapped every traffic flow, this is basically what the spaghetti diagram would look like. Now, if you had to design a point of use layout, ideally, if you were building a new facility, you go through some stages of analysis. This is your point of use. So you can see that the assembly work center, 761 ASY, the MIG welders, the final assembly here, they're all point of use. This spits out into the main assembly area. This spits out in the main assembly area. The MIG welder shoves things into the wheeler breaders area. The spot welder and the polishing station, they automatically send their components to the 761 assembly work center. So this would be the point of use configuration of this facility. Of course, we worked with them after they had built it. It was not that we wanted to say, oh, you did not get it right the first time. The issue would be, okay, next time we build a new facility in China or Vietnam, wherever, create the value network map and design a logical layout of the facility. Something which Taiichi Ohno said, something which John Costanza, maybe after reading Taiichi Ohno's book, figured out was correct, and then something which I, after reading Ohno and Costanza's book, also agree that, hey, you're right. So this is step number 3 in the lean thinking process, a point of use facility layout designed using value network mapping. But you see, what the layout does at best is it simply simplifies the logistics of flow management in a complicated facility. You still have to schedule production. Why? Because there are many components going through many shared resources. And I don't think you can do it by hand. So even if software tools like Preactor or Optisol or Tactic may schedule heuristically, at least they do feasible capacity constrained scheduling. Let's do that rather than use wrong methods like value stream mapping and takt time and Kanban squares and Hijinker. So this is the step 4 in the lean thinking process. How do you do pull scheduling but in a complex make to order network of value streams where they all share, many of them share common resources and they have unequal work content at various work centers. So this is what, you go back to the operations process chart, but remember in the bill of material I had named the product at various levels of assembly. So this is the final product, this is 22. This is value stream element 22, that has its own scheduling work content. This is the portion 20, so that means when this one had to be scheduled, how was that scheduled compared to this 11? So this has to be scheduled, this had to be scheduled. So think of these numbers as corresponding to jobs, and this whole collection of jobs corresponding to job 22, the final product. How do you schedule these individual jobs? So jobs 1 through 22 are like your jobs that are being scheduled using a job shop scheduling software. Okay. So again, over here what I did was same chart, but now if you notice in each operation I've put the process times. This is not good enough. I think that I would have liked to see a changeover time, a per piece cycle time, but again, we are learning, and as we figure out what we failed to catch the first time around, we are able to give you advice later. But this was the previous operations process chart. This is basically now saying, well, for each step associated with each job, tell me the total process content. Okay. So first approach was scheduled by hand. So all the work centers are listed here, and what you see here, this is Excel. This was the work of a team of industrial engineering students back when I taught ISC 542. That's our core course on production control and scheduling. Naturally, this was a take-home assignment for the entire team over the weekend. This was part of a quiz assignment. but they did a wonderful job. They correctly synchronized various jobs. So these numbers here represent, on this particular work center, you do job 1 in the value network map, then job 3, then job 2. Okay, and this is the time when it completes. So at the end of it all, what matters is, when did job 22 complete? So in an ideal state, with no delays, no interferences, no quality problems, it would have taken about 5.63 hours to make this entire value network map complete. So this is your goal state. This is basically saying, how do I schedule the various work centers, given that the various work centers are common. So for example here, see, you saw over here that this particular work center had to choose between doing job 1 in the value network map as opposed to job 3 as opposed to job 2. Something had to give. 2 had to wait for 1 and 3 to be done. 3 had to wait for 1 to be done. This cannot be done with Toyota Lean tools, period. This is essentially what industrial engineering and operations research have solutions to: complicated finite capacity scheduling problems. So this was done manually. This is the most important number. What is the best we could do if everything went well? Anything higher than this is an opportunity. So instead of 5.6 hours, if you noted 3 weeks, or you noted 10 days, that gap between 10 days and 5.6 hours is your opportunity for improvement. The same schedule, we kind of coaxed Microsoft Project. Why? Because any assembly is like a project, right? I mean, just as in a project, multiple activities have to be done before another activity can continue. Same thing in fabricated products. You can't MIG weld something. You need at least 2 components to weld. If one of them is missing, you can't weld it. And then similarly, if you've got shared resources and you have only one piece of that resource, if that resource is busy with job 2, you can't load job 3 on it. Job 3 has to wait. So people might say, well, Microsoft Project can't do scheduling. Well, I disagree. I think that if you had to teach people that scheduling is important, and you had a simple $300 package, which is a single license of Microsoft Project, I think you can tell them how value network mapping and this whole problem of synchronizing and prioritization of competing value streams which share the same resource, you could do all of that. So, again, even with Microsoft Project, what you saw done by hand using Excel, is basically what was done using Project. And this again, this whole total duration, think of this as a critical path with resource constraints factored in. Please don't believe that Microsoft Project cannot handle resource constraints. That is only the limitation of the individual who says Microsoft Project can't do that. Of course, there are much better, resource constrained project scheduling softwares out there, but Project can be used to demonstrate that value network mapping is viable and works. Of course, my favorite is Preactor. It's a finite capacity scheduling software. This is one of their value added resellers in America. Lean Scheduling Inc. is the other value added reseller that I work with. They are based out of Bradenton, Florida, and Mike Liddell is their president. But earlier I worked with Gregory Quinn, and he was very helpful, very obliging. He basically took the indented bill of routings and scheduled the same value network map. So what you see again is the same Gantt chart. And so as far as the contents of a value network map goes, this would be items 6 and 7. Item 6 is how to schedule and synchronize the production of the different value streams that require capacity on common work centers. So go back to 761 HMLV, go back to spot welder, go back to the MIG welder, go back to 811 assembly. Automatically you can see that this Gantt chart is telling you when various jobs that constitute the final product, job number 22 that is, how they'll be prioritized. And since you don't have 2 pieces of equipment of the same type, there's automatically a synchronization and a sequencing. So these Gantt charts effectively are doing item 6 which is in the value network map, how do you schedule and show the synchronization of various value streams which are connected to each other, because they will become a subassembly which will be one value stream. And if you look at the timeline here, that will probably be 5.63. So over here, if you look at this number here, this is the full Gantt chart almost. Okay, so if you look at the work centers where multiple jobs are being put, you're effectively being told with this visual display which one goes first and which one goes later on those resources, and the total timeline is the make span, 5.63 hours. So with the combination of group technology, production flow analysis done using FAST, layout design, and finite capacity scheduling of the total facility, making this product or a family of products, you have essentially the coming together of the value network mapping methodology. And the last element of the value network map, based on what value stream maps provide, is the value added ratio. That's number 7. How to compute the value added ratio for the entire network. Effectively, that's the duration of the critical path. How much time did it take for this overall schedule to complete? So 5.63 hours divided by how much time today it takes for the same value network map to complete, that ratio, the more you build that ratio towards 1, which means that you eliminate all the waste, you try and reach the goal of 5.63 hours, that becomes your, the holy grail. So effectively what we have done is, we've shown you the total value network mapping method, and you please judge for yourselves if with this method we have fulfilled all these objectives similar to what value stream mapping provides. I don't think that you need to have a pretty map. I think you need to have something which does the work for you. So I'm not very much about spending time to create icons and drawing value network maps which will take the entire wall or the room. My thing is that just as value stream mapping works for assembly, I would like to make a similar method, value network mapping, work for any high mix, low volume, make to order, complicated production facility. So if you use PR4, you effectively are able to do these 5 goals through a combination of FAST, layout design strategies, simulation software, and then 6 and 7, actually even 5, 6 and 7. So 1 through 5 you would do with FAST, and then 5, 6 and 7 you would also do with finite capacity scheduling. So pretty much what we are doing today is we are partnered with Lean Scheduling Inc. That's my Little's company, and we are partnered with Preactor International. They sell the finite capacity scheduling package. So between FAST and the plugin to Preactor, we have the ability to implement value network mapping. This is not to take away from what it takes to implement technology solutions, but the idea is that with value network mapping and the software tools to implement the method, we have a feasible blueprint for any high mix, low volume manufacturer, any job shop, to essentially not only become lean, but also flexible. So hopefully in the future, most Fortune 100, 500, whatever companies, they will be using Toyota Lean for the high end of their value streams, and they will be using Job Shop Lean for the lower end supplier portion of their value streams. And the method they would use is value network mapping. Now, the holy grail. How do you extend this method to multiple bills of materials? We haven't yet gone there. We know how to do it. Effectively, it would be multiple value network maps. But again, how would you do it? This came out of Gallagher Knight, 1972 book. So decades ago, the Britishers had figured out that the way you do lean in any kind of high mix, low volume facilities, you take every product, you explode that into its components, take every product, explode it into its components, run all these components through a group technology part family formation analysis. Once you form your families of parts, F1, F2, F3, F4, create flexible cells to produce the families of parts. So F2 and F4 will get produced in this group, one flexible cell. F1, F3 will get produced in this group. So how would you use FAST? If I may hazard a guess, all you would do is take all the components from the various products you make, and in the part numbers that you create, put a little string which identifies or associates each part number with the final product it goes into. And then run that entire group of routings into FAST. When you get the families of parts, you will know if a family of parts is unique to a product or whether a family of parts is actually built up of components which will go into many products. So I think the solution exists, and why do I say so? Because of some information I found from an American author's book where he was basically talking about MRP, but he was talking about flexible bills of materials. And here's the idea that he had that I said, whoa, he has figured out how we would apply value network mapping essentially to multiple bills of materials. Here goes. So take all the bills of materials for all your end items. This is it. So end item breaks out into these components. End item breaks out into these components in subassemblies. This end item has these subassemblies, these components. So you see high-level subassemblies, and then as the subassemblies break out, so what you're doing is you would be kind of looking at capturing these routings. Maybe too much for an online lecture again. I'd be happy to field your questions offline if you get interested. But what the author very nicely said was, explode your different products into components and subassemblies, and then group them based on which components are, identical in their routings. So in fact, we did this for an aerospace engine manufacturer that will not be mentioned. But what this former student of mine did was, he created a spreadsheet where the rows of the spreadsheet were all the engine configurations that they assembled, and the columns of the spreadsheet were all the components that got customized and plugged into the various engine configurations. So imagine, instead of a product process matrix, now what you have is an engine versus components matrix. You can run that through FAST, you can run that through Minitab or SAS, a clustering software. The clusters which will come out will tell you these groups of components go into these groups of engines. And then appropriately, you could design the layout, or you could design the supermarkets, and you could have replenishment strategies which effectively will replenish common components for families of products. So with this initial description of the products, what the author did was, he formed families. So what he said was, this family A actually comprises end items 1, 4, and 7. Okay? So what you're doing is, you might be saying, with this analysis, what you might be saying, I will have one flexible assembly plant which will assemble these end products, another flexible assembly plant which will assemble these products, and so on. Could be pie in the sky thinking, but that's the whole idea of taking group technology and standardization and part family concepts and saying, hey, how can we design flexible assembly factories? How can we design flexible point of use facilities? How can we design flexible cells, flexible sub-assembly cells, flexible assembly cells? So when people start throwing words like quick response manufacturing and saying that, wow, it's a completely new approach, I think that our ancestors in the 50s and 60s had the same answers. We have refused to learn from what they did. Why? Because we are so enamored with lean the way it was done at Toyota. Why? Because automotive manufacturing is a big part of industry. All I'm saying is, Toyota has given us the solutions to the problems that may have sunk or prevented our adoption of the principles of group technology and cellular manufacturing and variety reduction, etc., 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 that were pioneered by the British, the Russians, and the Germans, because they have the answers to lean and flexibility for high mix, low volume manufacturing, while Toyota gave us the answers to lean and flexibility for low mix, high volume assembly manufacturing. And then once you have these, you have these product families, then you go back and identify the part families. So this is basically telling you how would you design flexible parts producing feeder cells which would then assemble into these flexible assembly lines. So between what the group technology gurus told us and what Costanza and Ono and this author of MRP for repetitive manufacturing has offered us, I think that we know how to extend value network mapping to design flexible assembly and feeder cells for families of products. And that pretty much does it for this lecture. Again, if you have, as always, this program made this research possible, and in fact it encouraged me to actually take the research and make it work in practice. So with thanks to the Defense Logistics Agency, to ATI, Advanced Technology International, to the Forging Industry Association, and to all the companies that worked with us. And as always, my thanks to all the students who worked with me, both undergrad and masters, as well as the PhD students who did the research that made all this industrial engineering a reality. So my colleagues, Dr. Ramnan and Dr. Shivpuri, Jin Zhao, Smart Kev Soko and Heng Huang, the 3 PhD students, National Science Foundation, Defense Logistics Agency, Advanced Technology Institute, and these companies. There are many more forges. We kind of worked or have worked well with about 15 of them, but TECT, Consolidated Industries, Urban Forging, Weber Metals, CIFCO, and Trinity Forge have kind of been with us for the long haul. And to all of you, thank you very much. That does it for the lecture.